Hey guys, my name is Didi Jimenez, and today we're going to go over the receptors of the autonomic nervous system. Okay, so to start off, let's get into the basics. There are two types of receptors, cholinergic and adrenergic receptors. Cholinergic receptors consist of nicotinic and muscarinic receptors, and adrenergic consist of alpha and beta receptors. Now, moving on, let's get more in depth. First, we're going to talk about nicotinic receptors, which, as the name says, are activated by nicotine. These receptors are found in postganglionic cells of all autonomic ganglia. Their response occurs when acetylcholine, ACH, is released from both sympathetic and parasympathetic preganglionic fibers. Once binded to ACH, nonspecific cation receptor channels allow both sodium and potassium to pass. Once open, the movement of these ions through the channels depends on electrochemical forces, which the permeability of this postganglionic membrane typically aids. Sodium has a greater net driving force than potassium. This is due to the fact that the resting potential is closer to the potassium equilibrium potential. In this receptor, the concentration and electrical gradient for sodium are inward, while potassium has an outward concentration that is almost balanced by an opposing inward electrical gradient. This results in acetylcholine being triggered, and thus the opening of channels where more sodium moves in than potassium moves out, causing depolarization, which then initiates an action potential in postganglionic cells. Moving on, we have our muscarinic receptors, which you can kind of assume they're activated by muscarine. These receptors are located on effector cell membranes of cardiacs and smooth muscles, and in glands. These receptors bind with ACH, acetylcholine, that was released from parasympathetic postganglionic fibers. They function in activating different G-protein coupled receptors pathway. Lastly, they can have an excitatory or inhibitory effect depending on the effector. Now, muscarinic receptors were short and sweet. Let's get into our adrenergic receptors. Adrenergic receptors, in my opinion, have the most parts to them. There are two classes for non-epinephrine and epinephrine. We have alpha 1 and 2 and beta 1 and 2. They are located all over. Alpha 1 receptors are in most sympathetic target tissue. Alpha 2 are mainly on digestive organs. Beta 1 are specific to the heart, and beta 2 are in the smooth muscle of arterioles, which are small blood vessels, and bronchioles are airways. As you can imagine, different receptors have different attractions. Alpha 1 and 2 receptors both have a greater attraction to norepinephrine than for epinephrine. Beta 1 receptors have an equal affinity for both norepinephrine and epinephrine, and beta 2 only binds to epinephrine. Like I said, this was a little more complicated than the other receptors, from having different distribution, different affinities, to now different forms of activation. Keep in mind though, all these receptors are coupled to G proteins. They just have a different pathway activated. In beta 1 and 2 receptors, activation causes target cells response as a result from CAMP, which is cyclic adenosine monophosphate second messenger pathways being activated. Alpha 1 receptors, after stimulated, elicit the desired response through IP3CA2+ messenger pathway. On the other hand, alpha 2 receptors, once binding to a neurotransmitter, inhibit CAMP. The last thing we're going to go over before looking at our case study is the response of the effector organ. When an excitatory response occurs, it results in the activation of alpha 1 receptors. If it's an inhibitory response, the receptors activated are the alpha 2. For beta 1 receptors that are again only in the heart, stimulation causes an excitatory response, while beta 2 receptors normally have an inhibitory response. So you can see here the location of alpha 1 receptors are mostly in the sympathetic target tissue. alpha 2, digestive organs, beta 1, the heart, beta 2, smooth muscle and arterioles and bronchioles. I created this little graph, got it sort of from the book to have it to present in an easier format, more easy to understand. Now we are going to look at the effect of beta-adrenergic and muscarinic blockade on spatial learning and strategic use in the water maze. This case study involved the use of male long rats being injected with propanol and scopolamine. These injections were given in single and in combination dosages. Just for background, propanol crosses the blood-brain barrier and antagonizes beta-1 and beta-2 non-adreneric receptors in the thalamus, neocortex, and hippocampus complex. In this study, the rats were pre-trained with no drugs and then attempted to get to a platform, and it only took 20 seconds. On the 5th day of their spatial training, drugs were administered to them, and it was found that it only took a maximum of 60 seconds. It goes without saying that as pre-training continued, the time would decrease, meaning they would acquire and made use of the needed strategies. For the naive rats that received SCO and naive rats that received both SCO and PRO, there were longer search times, but as training increased, search time decreased. Now taking a look at chart A. A and C show the hidden platform search time, and B and D show the periphery swim time. In both cases, there was a strong correlation because periphery swim time is a major component of search time. In figure 1B, this one here, we can see that drugs increase periphery time in SCO and PRO with SCO groups. On day 2, we see a decrease in periphery swimming as training continued, and all in all, the periphery time for our naive groups demonstrated no differences. The next paragraphs give us our direct and circle swims of our naive and pre-trained groups in comparison to our control group. In figure 2A, this one here, ooh, that was bad. We can see that drugs impaired direct and circle swimming in naive SCO and PRO plus SCO groups. In figure 2B, we see that drugs impaired both naive and pre-trained PRO plus SCO groups. Those are here. Moving on to our swim paths. We notice a poor performance of naive rats with PRO and SCO administered together after remaining consistent with great periphery swimming and longer search times. Naive rats with just SCO demonstrated good performance due to spatial training and showed the ability to learning something and implementing it despite having impairments on day 1. So our naive rats with both SCO and PRO showed an excessive periphery swimming, and the pre-trained rats with both SCO and PRO swam away from the platform, halfway in the swim. And on our other digital, this was our first one here. Now we're looking at this one here. We can see excellent spatial memory in naive and pre-trained rats with both SCO and PRO and just PR groups. Others swam excessively in periphery, especially naive PRO and SCO groups. With this being said, results showed associations between impairment in strategy and use of search time. There was no evidence of impairment of performance in either naive or pre-trained rats due to antagonism of beta-adrenergic receptors alone. On the contrary, antagonism of muscarinic receptors affected naive rats, but not pre-trained rats, on day 1. rats administered both SCO and PRO had impairments in both water maze strategies and spatial locating. Nonetheless, results did demonstrate a correlation between strategy impairment and increased search time. There was no evidence of selective spatial impairment for the direct and circle swim measure. With the help of control groups, researchers can conclude that high dosage of SCO and NA of PRO affected the central nervous system. The PRO10 plus SCO3, which is the amounts that were given, that group never experienced impairments in water maze strategies, meaning there was excellent retention, the use of strategies from pre-training, good spatial learning, direct and circle swims comparable to that of the control group. It was only day 2 that impairments on the direct and swim measure occurred, and this indicated that the combined beta-adrenergic and muscarinic receptors can produce a specific spatial reversal learning impairments in the absence of behavioral strategy or sensomotor impairment. With the help of pre-training, researchers were able to identify specific impairment in spatial learning in the absence of strategies, and it helped to identify sensory motor impairments when using an adequate amount of PRO and SCO. Well, the main point of all this was pretty much Alzheimer's, which doesn't come as a surprise considering the impairment of adrenergic and cholinergic functions often happen in patients with Alzheimer's, like wandering, inability to use landmarks, and purposeless actions, which were all seen in this study. That was a lot of information, but we have now reached the end of our presentation of autonomic system receptors. These are my resources. See you guys on the next one.